We're going to cover everything you need to know about proofs in discrete mathematics. We're going to talk about the 5 different kinds and do a total of 9 examples explaining all of the steps. So the 5 types you'll have to do are direct proofs, proof by cases, which is usually embedded in another type of proof, proof by contraposition, proof by contradiction, and mathematical induction. So just briefly explaining what each of these are. With direct proofs, normally you have a statement like if P then Q. So it's like an if then statement. So what you do is, in this case, you'll assume that P is true, and then using either definitions or using deductions or algebraic manipulations, you will prove that Q is true. So we say it's direct because we start with our assumptions and we use manipulations to get our result. Proof by case is a little bit different. Normally you're proving some statement like P, or maybe you're proving if P then something else. And what's going to happen is, in order to prove or deal with P, you're basically going to have to split it up into different cases. So you might have that P can be split up into R and S, and then you prove individually that each of these are going to give you Q. So it's like splitting up your assumptions into covering all the different cases instead of just doing it all at once. With proof by contraposition, if you want to prove a statement like P arrow Q, what you're really going to be doing is assuming not Q, so assuming that the consequent is false, and then showing not P. So this is just the contrapositive law in logic, and it's going to be the same way as a direct proof. We're basically just going in the opposite way and having it negated. Now, with something like a proof by contradiction, normally we're just trying to prove something P. Now, what we do in a proof by contradiction is we assume that not P is true, and what hopefully is going to happen is we're going to get some other contradiction. So if we assume that not P is true, we're going to get R and not R, and then that is going to tell us that P is true. So in other words, this bit right here would be impossible because we get a contradiction, and we'll see that in action. And finally, mathematical induction is all about ladder proofs. So you want to show that some pattern goes on infinitely for integers, and these would be positive, well, greater or equal to 0. So let's just be consistent with this. So what you can do to do mathematical induction is basically establish 2 things. What we want to do is we can establish that a ladder can get off the ground. So we call this a base case. In other words, it needs to have a base. And then what we do is we show that later in the ladder, if we have an arbitrary step, then we can get to the next arbitrary step. So if this is step K, this means that we can get to step K plus 1, and this is going to be our inductive step. And if we can prove that both of those things hold, then we know that this goes on infinitely because we have a base, and because whenever we are at a certain step, we can get to the next step. So these are the 5 types of proofs. Let's do some examples. First proof, if x is an even number, then x squared minus 6x plus 3 is odd. So to do this, this is of the form P arrow Q. So what we can do is we can say, assume x is even. Okay, so now what we can do is we can work algebraically or with manipulations. So what I know about a term like x being even, and this might be defined in number theory, is that x is equal to 2 times a, or sum a in the integers. So basically what this means is that we're always going to get an even number. So if a is 0, then x is going to be 0. If a is 1, x will be 2. If a is 2, x will be 4, and so on. So this is the definition of an even number. On the side, if you want a definition of an odd number, that would be writing a number as like 2a plus 1. Okay, so we have this definition. So let's take x squared minus 6x plus 3, and let's plug 2a into it. So this is going to be the same thing as 2a squared minus 6 times 2a plus 3. If we factor this out, we're going to get 4a squared minus 12a plus 3. Now, I need to try to get it into the form of 2a plus 1 because we want to show that it's odd. So what I can do is I can do some manipulations here. I can first say that this is going to be 4a squared minus 12a plus 2 plus 1, just so I can get a factor of 2 coming out. So this is 2 times 2a squared minus 6a plus 1 outside. So this right here is of the form 2 times x plus 1, which tells us that this is odd. So by using the definition and our assumption that x is even, we have shown that x squared minus 6x plus 3 is going to be odd, just looking at the form. So this might seem like, how do I know what to do? Well, the thing is, you need to see a lot of proofs in order to understand what to do, because we have goals. What I said what our goal was here was to show Q was true. To show this is odd, I give a definition of an odd number, so we're trying to do algebraic manipulation to get to that form. And that takes some time and some practice. Let's try another direct proof. Show that for x and y being positive numbers, if x is less than or equal to y, then the square root of x is less than or equal to the square root of y. So this is our P arrow Q. So what we can do is we can assume that x is less than or equal to y, and we want to show, or at least our final step should be, that the square root of x is less than the square root of y. And we want to do this with algebraic manipulations without just using the square root symbol. We're not just going to take the square root of both sides. We're going to go with some definitions and some algebraic manipulations. So what we can do with this one is, if we have x is less than or equal to y, we know this is the same thing as saying that x minus y is less than or equal to 0. We're just subtracting y from both sides. So we might also think about working backwards at the same time. We might want to end up with the form of the square root of x minus the square root of y is less than or equal to 0, because that will give us our next step if we add the square root of y to each side. How are we going to get from our initial step to our later step? Well, this is where we might have to be a little bit creative. So what I'm going to do is I'm going to factor x minus y, because this is a difference of squares. So we know this is the same thing as the square root of x minus the square root of y multiplied by the square root of x plus the square root of y, and that's going to be less than or equal to 0. So what we also know is that x and y are positive numbers. So this term is going to be greater than or equal to 0, which means that we can then divide both sides by the square root of x plus the square root of y. And what you get from that result is that next step, and then we can make that further step to show that therefore the square root of x is less than the square root of y. So even though this is a direct proof where we're going from one step at the beginning to the last step at the end, I'm still working backwards in some cases just to see what I need to get. The reasoning has to go from beginning to end when you write up the proof, but sometimes you need to look at the end and work backwards in order to figure out what you should be doing. One more direct proof. This is a set theory proof. So let's say we have three things. We know that A is a subset of B union C. We know that C is a subset of D, so we only know two things. And what we want to show from this is that A is a subset of B union D. Now, we could do this just by using pictures, but I want to do this formally. So how we do a direct proof in set theory is we basically want to show this bit right here. So we're going to assume that X is an element of the set on our left. And what we want to do is we want to show that X is an element of the things on the right. We also have some definitions. If we have a subset relationship, we know that A is a subset of B union C. This says that X is in B or X is in C. And if C is in D, this implies that if X is in C, then X is in D. So we're going to use these definitions in order to get what we want. So let's just assume that we have X as an element of A. Now, what do we know? Well, A is a subset of B union C. Therefore, X is an element of B union C, which is the same thing as saying X is in B or X is in C. Well, we know that if X is in C, we're going to get that X is in D from the fact that C is a subset of D. Therefore, we know that X is in B or X is going to be in D. So therefore, we have that X is going to be in the union of B and D. So with our assumption, we have gotten to our conclusion. Therefore, we can claim that A is a subset of B union D. I have an entire video on set theory proofs if you want to see. I just want to show the direct nature of this, where we start with an assumption and then we just work going forward to get that final result. Now, those are direct proofs. What you might have to do in a direct proof is a proof by case or proof by cases. So here's an example. If two integers have the same parity, then their sum is even. So what this means is if we get an odd plus an odd, we're going to say that this is even. And if we get an even plus an even, then this is also going to be even. The thing about this is that we need to look at these two cases separately because we have to consider the different types of numbers. We have to consider when the integers are odd and the integers are even. We can't just do this in one go. We need to split this up into cases. So let's prove that odd plus odd is even. So let's say that this is 2a plus 1 and this is 2b plus 1. for an odd number. We're going to add these together and we need to show that it's even. So this is going to be the same thing as 2a plus 2b plus 2 if we add these together, which is the same thing as 2 times a plus b plus 1. And this right here is in the form of 2x, therefore this is going to be even. So that's the odd case. But what about the even case? Well, let's assume our first even number is of the form 2a, the second even number is of the form 2b. If we add these together, we can factor out to get a 2, and have that be 2 times a plus b. This is of the form 2 times x, therefore this is even. So because both of our cases came out to be even, we can claim that the entire thing is true. If two integers have the same parity, yes, it is even, and the proof is complete. Right, another example of proof by cases. For all real numbers a and b, if ab equals 0, then either a equals 0 or b equals 0. So what do we have here? We have this as an assumption. We have that ab is equal to 0, and then we're going to prove that q happens. But we need to consider our information at the beginning. So what I want to do is I want to ask myself, okay, we know that ab equals 0. So I'm going to split this up into two cases. I'm going to ask myself, what if a is equal to 0? And 2, what if a is not equal to 0? Because that will cover the whole case. And the reason I want to do this is because if a equals 0, then we can't do any division by a. But if a is not equal to 0, then we can make use of division to hopefully get something. So here's the thing. If ab equals 0, and we assume that a equals 0, then clearly a equals 0. So that part is done. That is satisfied. We don't care what b is because a equals 0. That satisfies things. That's also the nice part about breaking this up into cases. But what if a is not equal to 0? Well, if ab is equal to 0 and a is not equal to 0, this means that we can multiply both sides by 1 divided by a. And if that happens, what is our result going to be? We're going to get b is equal to 0, and we are done with this case. Now, you might be asking, what about cases 3 and 4, where b is equal to 0 and b is not equal to 0? We do not have to do these because we have a symmetrical argument. ab is equal to 0, then a is equal to 0, or b is equal to 0. If we were to change these around, say ba equals 0, then b equals 0, or a equals 0, we'd have literally the same argument. So whether we chose a or b, it doesn't really matter. But this is what we've shown. So that's the second proof by cases. Let's now talk about a proof by contraposition. So this is when we have a statement like p arrow q, and we're going to instead prove not q arrow not p. So this says if a squared is not divisible by 4, so if 4 does not divide a squared, then it says a is odd. So a is equal to like 2x plus 1. Okay, so what we're going to prove is the opposite. So this is our q, this is our p, so our not q is going to be a is even, because that'd be the same thing as saying a is not odd. And then this says that a squared is divisible by 4. So 4 divides a squared, and that would be our not p. So we can just do this proof as normal. So we can say assume a is even. So this means that a is equal to, let's just use 2x for some x in the integers. Now we're saying that a squared, if we square this, it's going to be the same thing as 2x squared, which is the same thing as 4x squared. Now, what do we know about our final statement that a squared would be divisible by 4? Well, we can factor out of 4, I mean, this is really just a pointless step, is equal to a squared. But with this definition, because a squared is equal to 4 times m for some integer m, we know that 4 divides a squared. So this tells us that 4 divides a squared, so the proof is complete. We just did a proof by the contrapositive, which was much easier. So if a is even, then a squared is divisible by 4. That's a much easier way to approach it. For our proof by contradiction, our first one, we want to show that if a is irrational and ab is irrational, then b is also irrational. Now, in terms of the definition of a rational number, what this would mean is that a is equal to m over n, so this would be a fraction where we say that m and n are integers in lowest terms, and we don't want to be dividing by 0, so we want to make the claim that n is not equal to 0. Now, in terms of an irrational number being defined, we just say that it can't be written as such. So this might be a little bit hard because a is rational, ab is irrational. We want to show that b is irrational. but like, what is a definition for this? So what we're going to do is we're going to assume what we're given. So A is rational. So we know what that means. We're going to assume AB is irrational. In other words, we just know that this cannot be written as a fraction. And for contradiction, we're going to show, instead of just directly showing that B has to be irrational, we're going to show B can never be rational. Because if B can never be rational, that means it must be irrational. So what we'll do is we're going to assume that it's rational and then find a contradiction with our assumptions. So in other words, we know that A times B can now be written as M over N, and let's define P then, B, I'm thinking of P ahead already. So let's define B as being P over Q for P and Q into integers and Q not equal to 0, because we're going to assume that B is rational. So let's assume B rational. Show that's impossible. So A times B would then be equal to M over N times P over Q. But this means that we have a number MP over NQ. And all we really need to do in this case is say, okay, I'm going to let C be a number being MP. I'm going to let D be a number being NQ. And suddenly we have AB being written as a form C over D. So this says that if B is rational, then AB is actually rational. But this is a problem. This is a contradiction because we assumed earlier that A times B is irrational. So if we assume the opposite of the result we want, what we're going to get is a contradiction. We're going to get something that our assumption just doesn't make sense. So that would be the end of the proof. Because AB is rational, we know that B can never be rational. Therefore, B is going to be irrational. All right, let's try another one. There is no smallest positive real number. So this is just a statement P. So what we're going to have to do for contradiction is just assume not P. So there is a smallest real number. Now we have to somehow get a contradiction out of this. So what are we going to do? Well, let's call this number R. Now, here's what I'm going to do. I'm going to say that it's a positive real number, so we're going to specify that specifically. It's not in the integers, it's in the real numbers, and it's positive. So we know that R is going to be greater than 0. But I'm going to say that we're going to create a new number S. And we're going to define this as R divided by 2. Well, then what's going to happen is 0 is going to be less than R divided by 2, which is less than R, which is the same thing as 0 being less than S, which is less than R. Therefore, S is smallest. But here's the thing. We just assumed that R was the smallest real number, and then we just found a number S that was smaller. So we have a contradiction. R is no longer our smallest real number if we assume that it is, because we can create one that's smaller. Therefore, there is no smallest positive real number. And that is how we do a proof by contradiction. One last type of proof is mathematical induction. So what we do is, let's say we have a formula, 1 plus 2 plus 3 plus all the way up to n, and we want to show that this is n times n plus 1 over 2. I believe that is the correct formula for that. 1 times 2 over 2 is, yeah, okay. So it is n times n plus 1 over 2. So in other words, what we need to show first is, does this hold for an infinite amount of numbers? So we need to establish basically a ladder. So we want to say that 1 would be equal to 1 times 1 plus 1 over 2, which would be equal to 2 over 2, which is 1. So in other words, we want to check when n is equal to 0. In terms of a diagram, this is like getting off the ladder. We want to show that we can get on. Now, as we go further, what we want to show or assume is that n equals k is true, and we want to show that we can get to the next step, n equals k plus 1. So we want to show in this case that 1 plus 2 plus 3 all the way up to n, sorry, this shouldn't be n, this should be k plus 1 is equal to, and then we'd replace all of our n's with k plus 1. So this would be k times 1, k plus 1 times k plus 2, all the way over 2. So we need to show this happens, and we'd be using our assumptions about n equals k to show that that is in fact true. So for example, we know that this bit is equal to Again, I'm not using n's here. This would be k times k plus 1 over 2, and then we're adding k plus 1. And if we do the manipulation on this algebraically, we would get to this step. So let's show one with a full proof. So I want to show that n is less than or equal to 2 to the n for all natural numbers. So for the base case, I need to show that this is true for the first natural number, which would be 0. For some people, that's 1. If it's 1 for your professor, it's 1. I was taught 0 as a natural number, so that's just what I use on the channel when I'm choosing my own preference. Okay, so is 0 less than or equal to 2 to the 0? And the answer is yes, because 0 is less than 1. Okay. So now what we need to do is we need to assume that n equals k is true as our induction hypothesis. What this means is that k is less than 2 to the k. This is just a fact that we can use. So now we need to show that n equals k plus 1 is going to be true. So let's start with 2 to the k plus 1. And what we want to do is basically we want to show that 2 to the k plus 1 is going to be greater than k plus 1. Okay, this is just substituting in k plus 1 for n's in our original formula. So we know that 2 to the k plus 1 is the same thing as 2 to the k times 2. And I want to do this because we have a fact about 2 to the k. We know that 2 to the k specifically is going to be greater than just k. So 2 to the k times 2 is greater than 2k. Okay, but we want 2 to the k plus 1 to be greater than k plus 1. So maybe we want a slightly different strategy for this, but let's just see what we can do at this point. Okay, well, now 2 to the k is just the same thing as k plus k. Now, k plus k at this stage, because we just have an arbitrary step, this is going to be greater than k plus 1. Because k will be greater than 1 in this case. Therefore, we can claim that 2 to the k plus 1 is greater than k plus 1. All right, and because we've shown our base case and our induction hypothesis to be true, we have therefore proven the entire formula. So that was a quick and dirty intro video to proofs in discrete mathematics. I do have longer videos that go over each of these individually on the channel, as well as plenty more examples. So if you want more details, you can always check those out. If not, I hope this video helped.